Hi folks, we're going to take a look at the last question from the related rates sheet. So here, the one we had started in class. So here it says water runs into a conical tank at a rate of 0.9 meters cubed per minute. Okay, so essentially what they're telling us, since this is meters cubed per minute, this is going to be the rate at which the volume of the water is increasing since it's going into the tank. Okay, so the tank stands point down and has a height of 3 meters and a base radius of 1.6. How fast is the water level rising when the water is 2 meters deep? Okay, so I'm going to draw my picture here, and instead of drawing an actual cone, I'm going to draw a cross section. So my cone in cross section is going to look like just a triangle. Okay, and we know that the radius is 1.6, and we know that the height is 3. Okay, so now I've got water going in at 0.9 meters cubed per minute. Okay, and of course when the water pours in, well, as it fills up, essentially the shape of the water is just going to be another little cone. Okay, so as I'm filling it up, the water itself is going to have the shape of a cone. Now again, even though they're giving me this 2 meters, okay, the water level is changing, so I want to keep it a variable while I'm solving this problem. Okay, so here we have that the volume of the water has a radius, or the cone that represents the water has a radius of r and a height of h. Since this is changing, I want to keep them variable. Okay, and what I want to know is how fast is this level, the height, water level, increasing as I keep increasing the volume by 0.9 meters cubed per minute. So that means the relation, okay, the related rates here are the rate of the volume and the rate of the height changing. So we have a volume formula for a cone, which is V equals pi r squared h divided by 3. Okay, 1/3 the volume of a cylinder with the same radius and height. Okay, and the problem here is that I want to relate volume and height. Okay, yet I've got this radius variable hanging around. Okay, so like we've had to do in the past, I need to find a way to eliminate this radius variable from my equation. Okay, and this is where now I need to use the constraint, the fact that this water is being poured into this particular cone, and see if I can come up with something. Okay, and one very useful geometric trick, so in the same way that in the previous problem we were able to use Pythagoras because we had a right angle triangle, here I want you to notice that I've got two similar triangles here. Okay, there's one triangle and then this bigger triangle here. These two are similar. Sorry about that, still coughing away. Okay, so when we have similar triangles, the relationship they have is that the ratio of the sides are going to be equal. Okay, so if I take the ratio of this side of the smaller triangle over the side, what's the word I'm looking for? Its corresponding side on the larger triangle, so r over 1.6, that's going to be equal to the ratio of this height side to its corresponding side on the larger triangle, which would be the whole height of the cone. So r over 1.6 is equal to h over 3. Okay, and then from this I can solve for r in terms of h. So 1.6 divided by 3 times h. I'll just leave it like that for now. Okay, and now I can input this into my equation. So volume is equal to pi times, so this is just 1.6 over 3 squared times h squared. So I'm just squaring this expression times the height, which is in the formula, and of course all divided by 3. Okay, so let's simplify this here. So pi times, I'll square this out, so 1.6 squared Okay, this 3 squared is going to go in the denominator, so 3 squared times 3 is 27 times h cubed. Okay. So now I've got an equation relating volume and height. So now I'm going to take the derivative of both sides with respect to t. And as we see in most of these related rate problems, our values are functions of t. So this whole thing is just a constant. Okay. So now I have to take the derivative of h cubed with respect to t. So first it's the derivative of h cubed with respect to h, so 3h squared times the derivative of h with respect to t. Again, just applying the chain rule. Okay, and when I take this derivative, I see that I still have this variable h. So that's why they needed to give me this extra piece of information, that we're looking for the rate of change of the height at the exact moment where the water is 2 meters deep. That's when the water has a height of 2 meters. Okay, so let's stick that in, and let's stick in the fact that we know that the volume is increasing at a rate of 0.9 meters cubed per minute. Sorry again. So here we've got here, listen, 3 and the 9, or the 27 and the 3 reduced to 1 over 9. So here I'm left with pi times 1.6 squared over 9, and so here h is equal to 2, so 2 squared, 4, and dh dt is my unknown. Okay, and now I can solve for dh dt, and let me do this carefully on my calculator here. So let's start 0.9, so I'll bring the 9 over to the other side, so times 9. Okay, and then I'll divide by 4. Okay, then I'll divide by pi, and then I'll divide by 1.6 squared. Okay, and here it looks like we get 0.25. Okay, we'll take it to 2 decimal places. Okay, and what are our units here? Well, the height was given in terms of meters, so this is going to be meters, and the time value was given in terms of minutes. Okay, so the height is increasing at a rate of 0.25 meters per minute as the volume is increasing at a rate of 0.9 meters cubed per minute. Okay, so again, just to recap, okay, setting up the diagram was very important, because we needed to notice how we could use similar triangles to write one variable in terms